Welcome to physics number 113. Today we're going to be looking at part 1 out of a lot of parts. Hypothetically, it would be 12 or 6 or something. But today we're going to cover the relativistic derivation of kinetic energy, or at least a tiny part of it, because the actual thing is huge and a monstrosity. So yeah, today is probably only going to cover a little teeny part of it. Anyways, today we're going to start out with this. So let's first start out with the normal, regular, non-relativistic derivation of kinetic energy. Because come on, relativity is so hard to understand. Cut me a little slack, goddammit. So let's go back into the classical world of classical physics. How did we derive this weird-looking equation? Well, I'm going to tell you how we did exactly this. Well, via the work-energy theorem, we know that your work is equal to the change in kinetic energy. Therefore, delta KE is equal to the integral of the force dot product, the distance. Of course, in normal terms, this would just look similar to this stuff. But remember, we're trying to look for this equation. And by the way, f times dx, this may look a little familiar to you from the equation work equal fd slash fx, depending on how you want to interpret the symbol. However, in calculus, when you're in calculus and using integrals, an x is a necessity for distance, because using a d will just get you confused with this other d type of d, which is actually basically a substitute for gamma, which means change in. So they're all synonymous. Just want to tell you. Well, sort of synonymous. By the way, d also kind of means derivative. So just wanted to point that out. So now, oh yeah, derivative is changing. So it is also derivative, but everything's synonymous. You can really see it. So now, let's see what we get if we zoom into this equation. Well, we know the famous physics equation, right? You should have known this from day one. Delta V is equal to acceleration. So V equal to delta D over delta T. Now, the same thing applies here. V is equal to dx over dt. Now, this may not seem like much because we only have one piece of the equation, but fear not, we can make this clearer. We know that impulse is equal to force over times time. And if I remember correctly from one of our lectures in the 50s or 60s, I remember that we proved that J is actually equal to P. Impulse is equal to momentum in terms of constants and physics terms. So that means that Ft is actually equal to P. Meaning that if P equal Ft, which we can actually draw as this, which is the true definition, then we can write dP to be equal to dF, just F, there's no change, and then dt. Now that gives us just an F equal to dP over dt. And that's where the second piece of our equation comes from. So now we can tell another piece of the story. By the way, I just want to say something. Since you're integrating with respect to some distance, this is the differentiation, whatever you call it, and this is the integram, which is the thing being integrated, and this is the differentiator or something like that. Now, since we're differentiating across some kind of distance, why don't we create an arbitrary distance, delta x, which will be equal to xf minus x initial. Obviously, we write it in terms of limits when it comes to calculus. xi, xf, xi, xf, blah, blah, blah. Now, we have f is equal to dp over dt times dx. Now, you can see that dp actually breaks up into 1 over dp. By the way, I gave you proof earlier today that I'm not memorizing these like garble. I actually tried to understand all these equations. The regular lecture I was taking leaf from actually had no explanation of the relativistic derivation of kinetic energy. So here I am explaining it in 6 or 12 damn parts just for you guys. Anyways, we're going back to the lecture. So now, it's our new student again. Hi. Oh, it's not our new student. She's been with us for ages, trust me. For half the series, she's been with us. More than half, actually. Anyways, dx, I made a mistake here. So this is supposed to be equal to dp. This is supposed to be dt. And this is dx. Yeah, got it. Sorry. So delta ke is from xi to xf dp times dx over dt. And I think you recognize this. We can actually simplify this and make it dv. Now, let's show an example of the product rule, because that will help with the partial integration we have to do with this handy integral sign right here. Well, so the product rule, if I remember correctly, is equal to AB whole prime equals to A prime B plus AB prime. I learned that a few days ago. Anyways, that means if we take the integral of it, remember, the integral is like the opposite of a derivative. So, that means that when we take the integral of AB whole prime, that actually cancels out the derivative and the integral. However, since the derivatives here only apply to one object and not the whole group, we can't do anything to the integral. It's unbreakable. So time plus AB prime. So now that gives us AB is equal to a integral of BDA plus integral plus or minus. I don't exactly remember. I think it was minus. So yeah, it's kind of confusing. I think it was plus. It was plus. Sorry, my memory is kind of fuzzy. ADB. That's what we have in mind. So now, that gives us integral of ADB is equal to AB minus BDA. And remember, D is for derivative, constant, changing, whatever. No, not constant. Anyway, if we apply this to our real example, then we can actually see, let's say that A is equal to V and B equal to P for the sake of it. Because come on, B looks like P. If you tilt B upside down, it looks like P. Now, that gives us VDP is equal to VP minus PdV. Now, that's all we're going to do for this lecture, since the rest is wildly complicated and I want to save your life from that monstrosity. So, we could do one more part. Do you want to do one more part or not? Oh, you want to continue with the show? Oh, okay then, I guess. That's a very unfortunate answer, but I guess we'll have to end it off for today.